Simplex method, maximization. Okay, let me give you a little background about this method. We're going to be using this method because when linear programming involves more than two variables, or two variables but many constraints, graphing can be inefficient and possibly not even doable. So we're going to use the Simplex method. This was developed for the U.S. Air Force by George B. Danzig in 1947. And it's even used today in industrial planning, factory design, product distribution, networks, sports scheduling, truck routing, resource allocation. There's a lot of uses for this. Now, when we write our functions, the objective function and the constraints are no longer going to have multiple variables, although the objective function will still be equal to z. Instead, we're going to use x with subscripts. So, for example, we're going to maximize z equals 2x sub 1 plus 3x sub 2 plus x sub 3. And our constraints will be x sub 1 plus x sub 2 plus 4x sub 3 is less than or equal to 100. X sub 1 plus 2x sub 2 plus x sub 3 is less than or equal to 150. And 3x1 plus 2x sub 2 plus x sub 3 is less than or equal to 320. And it's also understood that all three of those variables are going to be greater than or equal to 0. Okay, our standard maximum form, and right now we're just going to be dealing with maximizing. A linear programming problem is in standard maximum form if, number one, the objective function is to be maximized, all the variables are non-negative, so 0 and up, all the constraints involve a less than or equal to, and the constraints on the right side, the constants, on the right side in the constraints are all non-negative. In other words, any constants on the right side of the constraints must be 0 or greater. Now let's work on setting up the problem. We're going to go back to the example that we mentioned earlier. And the first thing we're going to do is we're going to convert each constraint into a linear equation. Now to do this, we're going to add in a non-negative variable that is called a slack variable to each constraint. Now I'm going to show you what this looks like, and then we're going to make a couple comments about it. So here's what it's going to look like. First of all, our objective function stays the same. Now here is the first of our constraints. Notice that what's been done is after the 4x sub 3, we're adding an s sub 1, and we're changing the less than or equal to equals 100. We're going to do that for each of these. Now here's the second constraint. And notice we've got an s sub 2 here, not an s sub 1. So this is a different slack variable. And again, we've changed it to an equation. And there's our final constraint, and again, a different slack variable. And then we've converted to an equals. So the S1, S2, and S3 have been added in. All of the less than or equal to's have been converted to equal. And our variables, all of them, both the x's and the s's, are all non-negative. They're all 0 or higher. Now just a note about this. Like I said a minute ago, notice that a new slack variable is used for each constraint. So you have a different one for each equation. Now, why do we even do this slack variable thing? The purpose is to make up for the slack that may occur when you're converting the less than or equal to an equals. For example, if I change x1 plus x2 is less than or equal to 10 to x1 plus x2 equals 10, I may need something to actually make it total 10. Because remember, originally the total of the two numbers was less than or equal to 10. So if they were less than, you need something in there to take up the slack to make it exactly 10. And again, our slack variables, like our x variables, have to be greater than or equal to 0. Okay, so back to our problem. So now we have a system of linear equations, but all of the variables need to be on the left. So we're going to rewrite our objective function. We're going to change it from z equals 2x sub 1 plus 2x sub 2 plus x sub 3 to negative 2x sub 1 minus 3x sub 2 minus x sub 3 plus z equals 0. And you do need to put them in this order. You're going to see why in a minute. So now we're going to write the system as an augmented matrix. And there it is. Notice we've got columns for the coefficients on the x sub 1, 2, 3, the s sub 1, 2, 3, and then for the z. All right, the first 3 rows represent our constraints. The last row is the objective function. And those first 6 numbers on the last row are called the indicators. The z, the one that represents the z, is not included as an indicator, nor is the 0 at the very end of that row. So it's just the indicators are that final row for the x's and the s's. All right, we're ready to start using the simplex method. The matrix that we just created is called the initial simplex tableau. It represents a system of 4 linear equations in 7 variables, and as you learned in algebra, it's going to have an infinite number of solutions. In order to have a unique solution, you need to have the exact same number of equations as you have variables. We want to find a solution where all the variables are non-negative and z is as large as possible because we're trying to maximize z. What we're going to do is use row operations to replace the given system by an equivalent one and to eliminate some of the variables so that we can actually find a solution. And the first thing we're going to need to do is to choose a pivot. Now, pivot, in case you don't remember from matrix, the matrix unit in college algebra, pivot is a non-zero entry that will be changed to 1, while all the other entries in the column will be changed to 0. And we need to choose this pivot very carefully. So the first thing we're going to do is choose the pivot. And here's the method we're going to use. First, we're going to look at the indicators, which is the last row of the tableau, except for the last 2 numbers on it. And we're going to choose the most negative one. In other words, the one farthest away from 0 on the left. The most negative indicator identifies the variable that is to be eliminated from all but one of the equations. In this case, it's going to be x2. So you'll notice that x at the bottom of x2 column, we have -3. That is the most negative of the indicators. The column containing that number is called the pivot column. So the column under x2 is our pivot column. Right, so here we have our matrix. And now for each positive entry in the pivot column, we're going to divide the number in the far right of the column of the same row by the positive number in the pivot column. So remember, our pivot column is the column under x2, it's column 2. We're going to be dividing the 100 by 1, the 150 by 2, and the 320 by 2. By the way, if there are no positive entries in that column, then we have no maximum. So now we have, after we do our division, we have a 100, a 75, and a 160. The row with the smallest quotient, which in this case is the second row, is called the pivot row. Now we're not changing anything right now, we're just selecting our pivot. So we have our pivot column is column 2, our pivot row is now row 2, and the number that's in row 2, column 2, is our pivot, and in this case the pivot is 2. Now as we start our pivoting process, what you need to do to show your work is you need to write the matrix, and then next to the row that you are going to change, you need to write what you are doing to change that row. Now, you may use the row ops program in your calculator to actually do the calculation and get the new matrix, but you do need to indicate what you are doing in order to get the new matrix. If you don't have the row ops program in your calculator, please see me and I will download it for you. The first thing we're going to do with our matrix is we're going to multiply the second row by 1/2. That's going to make our pivot 1. And here's the result after multiplying by 1/2. Now our pivot is 1. We need to change row 1, column 2 to 0, row 3, column 2 to 0, and row 4, column 2 to 0. So we're going to do those one at a time. We're going to tackle the first row first. And what we're going to do that is we are going to add the opposite of row 2 to row 1. So we're going to do negative row 2 plus row 1, and that's going to go in place of row 1. Again, this is what you're going to do using the row ops program in your calculator. You're going to tell it that you want to multiply and then add, and then you can write the resulting matrix. Once you've done that, this is what you should have. Now our first row has a 0 in the pivot column, which is good. Now we're going to go to our third row. And what we're going to do to change our third row is we're going to add 2 times the opposite of row 2 to row 3. In other words, negative 2 times row 2 plus row 3. And now we've only got one entry we need to change, and that is the negative 3 at the bottom of column 2. So what we're going to do is we're going to multiply 3 times row 2 and add that to row 4. And here's the result of that operation. Our pivoting is now complete for the moment. This is called the new simple tableau. Now notice in all these things we did not interchange rows. And I know when you're working with matrices to solve equations that you can do that. We do not want to do this for the process that we're doing. Do not interchange the rows. Instead, multiply the pivot row by an appropriate constant, and then add or whatever you need to do. Now, here's the problem. We still have negative indicators. We have to continue to do this process or repeat this process until we have no negative indicators left. So, we're going to be choosing a new pivot. Now, the first thing you do, if you remember, is you find the most negative indicator, which is going to be negative 0.5. And then we are going to divide every entry on the far right by the entry in column 1 on the same row. So 25 divided by 1/2 is 50. 75 divided by 1/2 is 150. And 170 divided by 2 is 85. We then select the lowest of those quotients, which is going to be 50. And that tells us what row we're dealing with. So our new pivot is going to be 0.5. Now we're going to repeat everything we just did, but this time we're going to be using row 1, column 1 as our pivot. And the first thing we're going to do is change that pivot to equal 1. So in order to do that, we're going to multiply row 1 times 2. Our pivot is now equal to 1, and we need to change the rest of that column to zeros. So let's tackle row 2 now. We're going to multiply row 1 by negative 0.5 and add that to row 2. And here's our result. Now we're going to tackle row 3. And we are going to multiply row 1 by negative 2 and then add that to row 3. And that will give us a 0 in row 3, column 1. And finally, what we need to do is we need to multiply row 1 by 1/2 and add it to row 4. Okay, now we have our pivot is 1, everything else is 0. Also notice we have no negative indicators left. This is good news. This means that this is our final simple tableau. Time for celebration and time to finish the problem. The last row of our tableau gives us this equation. 4x sub 3 plus s sub 1 plus s sub 2 plus z equals 250. Or solving for z, 250 minus 4x sub 3 minus s sub 1 minus s sub 2. Now, if you look at this equation, remember, we want to maximize z. Z is going to be at its maximum when the three variables here are 0. Remember, they must be positive. So we can't have negative variables. Any positive number in there is going to give us a number less than 250. So if all three of those variables are 0, we're going to have our maximum value, and that maximum value is going to be 250. So what we're going to do is we are going to take the equations from our matrix, and we're going to substitute in 0 for x3, s1, and s2. So here are the equations that we got from our matrix, leaving out all of the variables that had a 0 in their place. If you go through these and you put in zeros for x sub 3, s sub 1, and s sub 2, you're going to find that x sub 1 is 50, x sub 2 is 50, and x sub 3 is 0, which we already said. The variables in the columns that look like the columns of an identity matrix are called basic variables. In our example, the x sub 1, x sub 2, and s sub 3 and z are all basic variables. If you look at those columns, they had a 1 and the rest were zeros. Those are basic variables. The other variables are called non-basic variables. Now this is going to become important when we move into our next section, and a very useful fact. So keep that in the back of your head. The columns where they look like the identity matrix columns, those are your basic variables. The others are non-basic. Okay, this is a summary of the simplex method, step by step. You determine your objective function, you write down all the constraints, convert each into an equation by using a slack variable, set up the initial simple tableau, locate the most negative indicator. It says if there are two that are the same, just choose one. That's going to pivot column, and then this just goes through the rest of the steps that we've talked about. Notice at the bottom it says in the final tableau, the basic variables correspond to the columns that have one entry of 1 and the rest 0. The non-basics correspond to the other columns. Here's a little tip. If you set each non-basic variable equal to 0 and solve for the basic variables, that gives you your answer. The maximum value is the number in the lower right-hand corner of the final tableau. All right, here are a few problems to try. If you will pause the recording, give them a try, then resume the recording to check your answer.